Hey, this is a lecture on graphing and linearization in physics. So linearization is just a fancy word for graphing some data, graphing some variables in a particular way to make our best fit line linear, make it a straight line. If we do this, then the gradient of our line, or the slope, and intercept may actually have some physical meaning. And we can use their values to figure out something about the universe or about something about our system. So what we do is we use theory, we use what we know to find a set of variables that we want to graph such that we get a straight line. And it's usually not going to be just the variables we measure directly. It's usually not directly the independent and dependent variable. Usually we have to process our variables to graph. Oops. Then we graph our data, and then we find the gradient of the best fit line and use it to determine our constants based on our theory. So in this lecture, I'm going to talk about kind of what linearization is in general, and then we're going to do an in-depth example for how it's used to find a physical constant. So let's say we're investigating Boyle's law, which relates the volume and pressure of a fixed mass of gas at a constant temperature. Well, we can measure the volume and the pressure simultaneously. We can get our raw data and we could graph it to see if there's a relationship. Now, Boyle's law states that pressure is inversely proportional to the volume. So pressure is proportional to 1 over volume. So we would expect, if we graphed our data, we would get something like this graph here, an inverse function. Now that would be great. That would confirm, at least appear to confirm, Boyle's law. But how do we know that this is an inverse function? And how do we know that it's not an inverse square function? Or how do we know it's not an inverse cube function? Or how do we know it's not some other function that is inverse in some way, but the power happens to be off? This is why we need to linearize. Another reason we need to linearize is, instead of thinking about this in terms of a proportion, let's write it as an equation. Well, a proportion just means that the left side is equal to the right side times some constant. So we could say pressure is equal to some constant divided by V. Well, if we could get the right fit curve to this graph, then we could figure out what this K constant is. However, it's really hard to figure out precisely what the right fit is going to be if we don't have a straight line. So we need to figure out how to graph this such that we can get a straight line. Because pressure is 1 over volume, we could actually rewrite this as either pressure is 1 over volume and 1 over pressure is equal to volume. Now these actually seem the same, but they are going to be physically different if we graph them. I'm not going to go into why we pick one or the other now, but just for now we're going to choose what's on the left. Or sorry, what's on the right. We're going to choose this one and graph this one. And remember, proportional just means the left side is equal to the right side times a constant. So 1 over P is equal to some constant times volume. So when we linearize, what we're going to do is we're going to graph, since we had 1 over P is equal to a constant times volume, we're going to graph 1 over P against volume. Now because 1 over P is proportional to volume, we should get a straight line graph. At least we expect a straight line graph. We expect something like this. The nice thing about graphing is if we don't get a straight line graph that goes through the origin, the offset might tell us about something in our experiment that doesn't align with our model. In this case, we do get a straight line graph, and we can use the slope of that to find our K constant. However, our intercept should be 0, because at 0 volume, our pressure should go up to infinity, which means 1 over pressure should be 0. However, in this case, it looks like at 0 volume, we don't have an infinite pressure. So 1 over P is not 0. This shows us that our graph is actually offset by this amount delta V from the true volume. And we could look at our system to figure out where that extra volume is. It turns out it's because there's going to be some volume that we weren't accounting for in our system when we took our data. So when we linearize, we just graph things in such a way that we get a straight line, and then the slopes and the intercepts can become physically meaningful. If we wanted to correct our graph, all we would need to do is graph P against 1 over V plus delta V. And then we would find our pressure is proportional to 1 over our effective volume. So we're going to go into a more in-depth example now for why is graphing and linearization important. We're going to use an example in which we're measuring g acceleration due to gravity. We'll talk about why we need a graph and why we can't just use numbers, how we determine what to graph, and actually how we're using this linearized data to measure our g value. Now, keep in mind that these techniques are going to be useful in any experiment. In any experiment, we can linearize and use the slope to find some stuff out. Anytime we can graph and get a slope, this is going to be useful. So here's our setup. We have a metal ball hooked up to an electromagnet that's turned on. When the switch at the top is closed, an electric timer is started and the electromagnet is turned off. When the electromagnet is turned off, the ball falls to the bottom and strikes another switch. This switch is opened, and when it's opened, the electric timer is turned off. So if we measure the height, we should be able to get very accurate times for our falling ball. So since we have a constant acceleration, we can use our equation, s equals ut plus 1/2 at squared. Our ball is dropped from rest, so u goes to 0. So we can rewrite this function as h equals 1/2 gt squared, where h is technically it's really the distance fallen, as measured as the height. And the drop time is gotten from this electric timer. So here's our raw data. We have 4 ordered pairs of data, which is really not enough data, but it works for this analysis to kind of prove what we're going to show of height against time. So one thing you might do, well, if we want to solve for g, we take our equation and we solve it for g. h equals 1/2 gt squared, so g is equal to 2h over t squared. So we might just solve for g for each different variation. Our first variation, we plug in our ordered pairs for h1 and t1. We get g is 6.30 meters per second squared. We do it again for g2, we get 7.09 meters per second squared. g3, we get 7.46 meters per second squared. And g4, we get 7.76 meters per second squared. If we take the average of all of these, g bar is equal to the sum of all the g's divided by the number of g's, we get 7.15 meters per second squared, which is not a good result. We know that gravity should be about 9.8 meters per second squared, pretty much on the surface of the Earth anywhere, whether it's in Montezuma or not. So averaging our data does not give us an accurate value. So this is why we're going to need to graph. So I took the data and I graphed drop height horizontally against time, and we get this function here. Now, it's hard to tell if this is linear or not, but we can fall back on theory in order to make an assessment. Theory suggests that it's actually not linear, because if we have h is 1/2 gt squared, then when we solve for t, it's going to be the square root of 2h over g, so it should be a square root curve. Square root curve is going to look something like this. And it looks like that square root curve is probably going to fit more than this straight line function. Notice that the points do look like they're curving down even if we do a best fit line fit. Now they're pretty close to a best fit line fit, but it looks like a square root fit might be better. And since we have a good theoretical basis for thinking it's a square root fit, then that's what we are going to look at and investigate. So we're going to test this out by linearizing our data. Instead of graphing time against drop height, we're going to graph some different variables. So again, if h is 1/2 gt squared, then t squared is 2h over g. So t is just square root of 2h over g. Another way of writing this is that t is equal to the square root of 2 over g times the square root of h. QED, t is proportional to the square root of h. And it's proportional to the square root of h with a gradient or slope of square root of 2 over g. We could think of this as y equals mx. So this is actually how we're going to linearize. We're going to compare our equation that we got from theory to the equation for a linear function. Y equals mx plus c, or often we write b instead of c. The variable that's on its own, we're going to graph in the y value. The other variable that we have measured that compares with c, we're going to graph in our x value, and the coefficient is going to be the slope. So we'll graph t against the square root of h. This is what we get when we actually graph our data. We do get a straight line. These are our data points here, 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 and here. There's a lot going on here. The gradient, the slope of our line, is going to end up being the square root of 2 over g. And that's going to take into account all of the data points for in order to calculate g. Notice that if we graph square root of height against time, when we go to a height of 0, which is also a square root of height of 0, we still have a non-zero time. And that doesn't really make sense in theory, because if we drop it from a height of 0, it should take 0 seconds to reach the ground. So this indicates a systematic error in time in our experiment. However, that systematic error in time might not affect my value of g if I graph my data. And in fact, it doesn't, because all of the data are shifted up by the same amount, which means it doesn't affect the slope or the gradient. So the blue line is what we would expect, and this black line is what we actually get. So this is our theory, and this is what we get in our experiment. Notice that their slopes are the same. So we can still set the slope equal to root 2 over g. We proved that the slope is root 2 over g from theory. And if we solve for g, we get, well, slope squared is 2 over g. So g is equal to 2 over the slope squared. And we only have one number for slope. We don't have to take an average or anything. So g is going to be equal to 2 over our slope squared, which is 2 over this value, 0.204, which is 9.79 meters per second squared. That agrees much, much better with the accepted value for the acceleration due to gravity. So g from our data, if we just calculated it raw from our data, was was quite far off. And this is because there are going to be systematic errors sometimes. But G from the graph ended up being quite accurate, because when we graph, the systematic errors do not affect the slope of the graph. And there are always going to be errors, and there might be systematic errors. We have to try and figure those out and take those into account. And if we do find a systematic error, we can go back to our experiment and try and identify where that systematic error comes from. In this case, it was a delay in dropping the object from our electromagnet. So in summary, we linearize in order to figure things out, figure physical constants out. So what we're going to do is we're going to use theory to write a function in terms of variables that can be measured. Theory as in equations. And we compare with y equals mx plus b to determine which combination of variables to graph on the x and y axes. We graph our processed variables to get a straight line function. Maybe we get something like this initially. We graph our processed variables, we'll get something that is a straight line. And then the slope or gradient of our best fit straight line can be used to determine our numerical constants. That's all. Bye.